Hello friends. Now in this lecture we'll be talking about reaction of beams. Myself Prakash Kadve, Principal K.K. Wag Polytechnic. Let us start with types of supports for the beam. So the supports can broadly be classified into two categories, simple support and fixed support. But further this simple support can be a hinged or pin support. And second one is a roller support. So let us see the first example, hinged or pin support. These are the two diagrams to explain it. Both of them are called as hinged or pin support. Usually in many books or question paper, you may get a picture like this. So both of the support means the same thing. Now what is important here? Here you have to see what kind of reactions get developed at this type of supports and is there any movement resistance or not. Simple support or hinged support is like this. The beam is resting at this end, but this end is acting as a hinge. In the sense, if I apply a horizontal thrust here, because it is hinged at this end, it will not allow the beam to dislocate from its position, means the beam will remain at this place only, will not move in this direction. Or even if I try to push it up, it will not move in the upward direction. But whereas if I apply load here, it can rotate about this end. It can rotate like this. So what is the meaning of this? That is, if I apply load here, so whenever I am applying certain load, there will be certain reaction. So that reaction gets developed at this end. Why reaction gets developed? Because on application of load, the beam won't change its position. It do not get displayed from its position. That means there is certain restriction on its movement. What is that restriction? That restriction is nothing but the development of reaction at the end. So this development, if I apply a horizontal thrust, it is not allowing horizontal movement, means horizontal component of reaction is there. If I apply a vertical load, it is not allowing the beam to get displayed in vertical direction, means vertical reaction is there. Or otherwise, if I apply certain inclined load, still it is not allowing the beam to dislocate from its position. That means this inclined reaction is also resisted by the beam, means at the end of the beam you can have one vertical component of reaction, other horizontal component of reaction. But as I told you, when I apply load, it can show the rotation of the beam in this direction like this anyway. So if it is so, that means this end is allowing the beam to rotate about the pin or about the hinge, means there is no resistance offered for the movement. That means movement at this end is zero. So what I mean to say, when I am applying load and if it is pin or hinged end, only reactions will be developed at the pin or hinged end and movement will be zero. The same thing is here, only how you show the pin end, either you can show this way or you can show this way. Roller support. Now what is roller support? See, these are again two examples. This is also one of the example of roller support. This is another. The difference is that here it is horizontal support, here it is inclined support. Now this is most important in roller support. In roller support always the reaction gets developed in the direction perpendicular to the support. So this is the direction of support. Perpendicular to the support means vertical to the support. Second example, this support is inclined, so reaction will not develop vertical, but it will get developed in the direction perpendicular to the support. So this way reaction will be developed. As like of this beam, no movement will be developed at the end. So therefore, movement about this roller support is zero. When you apply horizontal thrust, because of roller, it is likely to shift its position. That means there is no horizontal reaction. So reaction will be developed only in one direction, that will be perpendicular to the support. In this case this is vertical, but in this case it will be inclined. And next support is fixed support. So fixed support, you can see here, this is the support and the beam is embedded inside the support, it is fixed inside the support. So when it is fixed, it will not act like a hinge. So when I apply a load, there will be a horizontal component of reaction as well as vertical component of reaction. Since it is not allowing the beam to rotate, that means certain resistance is developed at this end against movement, and that resistance we call it as moment of resistance. That means fixed end is capable of resisting movement. In other words, you can say at the fixed end movement is not zero, but it has got certain magnitude. So at fixed end you get vertical reaction component, you get horizontal reaction component, as well as you get movement. Next, movement. What is movement? Movement, it is a product of force and a perpendicular distance from the force from the point about which the movement is calculated. Now see, with example we'll just see how it is. I will show you two different examples. Now see, this is the point and this is the force. I have to take moment about A. I have to calculate moment about A. Now what the definition says, moment is product of force into distance. But which distance? Distance which is perpendicular to the force from the point under consideration. So if this is the point, I have to draw a horizontal here because force is vertical. So this distance is called as perpendicular distance between them. So it is D. So moment about A will be equal to F into D. Force into distance D. Similar way I have shown here, the force is inclined here. Horizontal distance is D, but moment is not equal to F into D, because my definition says that it should be a perpendicular distance of the force from the point about which moment is calculated. So this is the point from about which moment is calculated. From this point, the perpendicular distance is this one, L1. So moment about A will be equal to force into L1. Or otherwise what you can do, you can take vertical and horizontal component and go on solving. This is same thing I explained in other way. See, this is the beam support A. This is the force F1 acting at distance x1. This is inclined force acting at a distance x2. I have to find out moment about A. Due to F1, it is simple. F1 into this distance x1. Due to F2, it will be not F2 into x2, because x2 is not a perpendicular distance. This angle is not 90 degree. So what I am doing, I am plotting a perpendicular from this end, and this distance is L1. So moment about A will be equals to F2 into L1. Next, let us see sign conventions. They are very important. So I am assuming this. The force going vertically upward, I am considering it as positive. Force going vertically downward, I am considering negative. You can change this sign. That doesn't make any difference in calculations. But this is a standard convention, we will just remember. Going up plus, going down minus. Same thing about movements. Now if I am taking movement about A, let us say this is the line passing through A. So if on right hand side, if the movement is clockwise in the sense the way the clock pointer of the clock moves. So this is called clockwise. So if it is clockwise on right hand side of the section, then it is positive. But at the same time, if it is on left hand side, then anti-clockwise will be positive. Same way here. If on right hand side anti-clockwise, it is now I am taking negative. But on left hand side, if it is clockwise, it is also taken as negative. The same thing I have shown here with different manner. So this is the section, let us say this is point A about which I am taking movement. So on the right hand side, if I am considering the forces, So clockwise movement will be positive, anti-clockwise movement will be negative. Or now, as I told you, this is not rule. You can change. You can have completely reverse thing. So you can consider, here it was considered plus, the same thing you can consider minus, negative. Then other way around, the another thing which was already earlier considered negative, here you can consider positive. But if you are using this thing, then what you have to do, if you are starting to solve the problem by assuming this convention, till end of the problem you have to maintain it. For first step you take this, and for second step you take this, will not do. Once you start with this assumption, you finish the problem with the same assumption. Or from beginning you take this assumption and finish the problem with this assumption. Next example, let us see. This is the beam AB having total span L. At center means L by 2. You have got a load acting with a magnitude of W newtons. Let us say this point as C. What you have to do? You have to find reaction at A and B. So these are the points A and B. You have to find what is the reaction. I am assuming at A, RA is the reaction and RB as the reaction at the end B. And I am assuming both are going vertically up. So in this diagram, if I am seeing RA and RB are the reactions, and if these are my assumptions, then accordingly RA is going up, you will be plus, RB is going up, will be plus, W going down will be minus. So as per these sign conventions. So we'll go ahead. What I have to do, I have to use conditions of equilibrium. I have got three conditions of equilibrium. Sum of all horizontal forces is equal to 0. Actually it is algebraic sum. So we'll call algebraic sum of all vertical forces must be 0, and algebraic sum of all moments about any point must be equal to 0. So here you don't have any horizontal force, so you don't require any condition of equilibrium, that is summation of horizontal forces is equal to 0. So you require only these two conditions. We'll use these two conditions. So first condition, summation of vertical forces must be 0. So I told you this is one vertical force going up. Since going up, as per this I am taking positive. So say plus RA. Then second RB. As per these sign conventions, again I am taking positive. So plus RB. W going down, so minus. So RA plus RB minus W is equal to 0. So you get RA plus RB is equal to W. This is equation 1. Now I am assuming clockwise and anti-clockwise movement on the right hand side of the section, clockwise plus anti-clockwise minus. So it is mentioned here, the statement is mentioned here. Now what I have to do, I have to take movement about any point. So let us say movement about A. So I am taking movement about A. So this is my section line at A. So all forces are on the right hand side. So I can use this sign convention on the right hand side of the section. So let us say this is A. Then these are the sign conventions. So W force, if I increase the force and if it rotates, it will allow the rotation in this direction. Means it is clockwise rotation. So it has to be taken plus. So what is, I am taking movement. Movement is what? Force into distance. So force is W, distance is L by 2. So I am taking sum of moment about A and it must be equal to 0. So what is the first moment? W into L by 2. So this is W into this distance L by 2. Second moment is this RB. RB into distance from A. This is L. This distance is L. So RB into L. But what is about sign? Now if I see, if it tries to lift the beam, it will have the rotation in this direction, which is anti-clockwise. So anti-clockwise is minus. So I am taking minus RBL is equal to 0. So you get RB is equal to WL by 2 divided by this L. You get W by 2 in newtons. So you get RB is equal to W by 2. So reaction at B is equal to W by 2. Similarly, if you put this value in equation 1, so I put this W by 2 in equation 1 here as RB. I get RA plus W by 2 is equal to W. So you get RA also equal to W by 2. So it is Here you can just see if load is applied at the center, half reaction will go here and half reaction will go here. So total load is W by 2 at A and W by 2 at B. This is what after calculation we are getting W by 2 at B and W by 2 at A. Similar way we will see one more example. Now this kind of load is called as uniformly distributed load. Uniformly means once the intensity is stated, same intensity will be there from one end to other end or the span on which it is shown. So it is shown over the entire span L. Its intensity is W Newton per meter. So it is not load, it is intensity of load. So if you have to calculate load, you have to multiply this load by the span on which it is acting. So if I am saying what is the load acting on the beam, so it will be W multiplied by L. So WL will be the total load. Now again same assumption, assume RA and RB as reaction at A and B. They are going vertically up. My assumption, vertically up plus vertically down minus. Use conditions of equilibrium. Again no use of this. I have to use only these two equations. So summation of all vertical forces must be 0. So I got RA plus RB plus, so I am saying RA plus RB minus. Now what is minus? W is the intensity applied over span L. So total load will be W into L. And this must be equal to 0 as per this condition. So therefore RA plus RB is equal to WL. Now what? Now just you have to take the moment. So for that assume clockwise movement or right hand side of section as plus. So here you can get more clear. This is my section. So here it is my section. At A I am taking movement. So on right hand side clockwise is plus, anti-clockwise is minus. So this W load is acting going downwards. So it will cause clockwise movement. So I am taking clockwise as plus and RB will cause anti-clockwise this way. So it will be minus. So movement about A, W. W is intensity, W into L is the force. So WL, force into distance. So L by 2, how it is L by 2? Now when UDL is acting, when you are multiplying it by span, you get total load, and it is assumed that the total load will act at the center of the span on which UDL is acting. Now here UDL is acting over entire span, so total load or point load will act at the center. So that way WL is the total load and multiplied by L by 2. Then minus. Now this RB will cause anti-clockwise, therefore minus. So RB into distance from A is L. So RB into L is equal to 0. So you get RB is equal to WL square by 2 divided by again this L. So you get RB is equal to WL divided by 2 in newtons. So reaction at B will be WL divided by 2 in Newton. If you put it in equation 1, you get RA plus WL by 2 is equal to WL. So RA also is equal to WL by 2. So reaction at A is WL by 2. At B is also WL by 2. Both reactions are equal. It is quite simple and can be seen from the diagram. If uniform load is applied over entire span, so half reaction will go to A and half reaction will go to B. Total load is WL, so half is WL by 2 at A and WL by 2 at B, which is also seen from calculations. Now next, eccentric loading is there. This load is not at center, but it is at certain distance A from left support and certain distance B from the right support. So similar here you have to find out reaction at A and B. Same assumptions I am going for, up force plus, down force minus. Then use conditions of equilibrium. So I have to use again only two conditions of equilibrium. So I will be using only two. Summation of vertical is equal to 0. Vertical forces is equal to 0. So how many vertical forces? Reaction at A first, reaction at B second, and this W third. First and second are going up, positive. W going down, so minus. So I will take RA plus RB minus W is equal to 0. So I can rearrange the terms. I get RA plus RB is equal to W You can call it as equation 1. Now you have to take moment about A. So when you are taking moment about A, again same assumptions. On right hand side of the section, clockwise is plus, anti-clockwise is minus. So here W force will cause clockwise moment and this RB will cause anti-clockwise moment. So I am taking summation of moment about A. So you can say W into A. So W into this distance A minus RB into L. So total length is L. So RB into L is equal to 0. Therefore RB is equal to, if I do the rearrangement of the terms, I get WA divided by L. So RB is equal to WA by L in newtons. So once I get RB, I can put this value in equation 1. So I get RA plus WL by 2, sorry, WA divided by L is equal to W. Again rearrange the terms. Here RA is equal to W minus WA divided by L. But what I will do, I will put this L is equal to A plus B. I am putting L is equal to A plus B. Actually L is LCM. So I will get the term WL minus WA divided by L. Put this L as A plus B. So you can solve, it will get WA plus WB because L is equal to A plus B minus WA the whole divided by L. So this WA gets cancelled. You get RA is equal to W into B divided by L. So this is W into B divided by L will be the value of RA. Now next problem, calculate reactions of the beam loaded as shown in the figure. So here you have got 3 point loads. Very simple problem, 1 meter, 1 meter, 2 meter and 1 meter. You have to find out reaction at A, reaction at B. We'll go with the same assumptions. Assume RA and RB as reaction at A and B respectively. Assume both are vertically upward. So I am taking upward plus and downward forces minus. So here you have got two conditions of equilibrium, summation of vertical forces must be 0 and summation of movement must be 0. So here I am taking RA plus RB vertically up, therefore both are plus, but all other are going down. So minus 20 minus 40 minus 10 is equal to 0. So summation V is equal to 0. From this you get RA plus RB is equal to 40 plus 30, that is 70. So it is 70 Newton. Now taking moment about A. So this is my point A. I have to take moment about A. So on right hand side of the A, you have got 1, 2, 3 and this as the fourth force. So these three will cause clockwise movement about A. I will take it as plus and this RB will cause anti-clockwise. I will take it as minus. So this is the sign convention. So you are taking moment about A. See, this is plus because it is clockwise. So 20 into 1. This is the first moment, force into distance. Second force is 40. 40 into this distance because we are taking moment about A. So 40 is placed at 2 meters. So 20 into 1 plus 40 into 2 plus this 10 into this distance, that is 4 meter, 10 into 4 minus RB because RB is going to cause anti-clockwise movement about A. So it will be minus, since it is anti-clockwise, force multiplied by distance. So 2 plus 3 5. So it will be RB into 5 is equal to 0. So by solving this you get RB is equal to 28 Newton. Put this value of 28 Newton in equation 1. You will get answer. RA plus RB is 80. So RA is equal to 80 minus 28. You get RA is equal to 52. Same problem, we'll solve it by graphical method. Again I am reproducing the diagram. Same spans I am writing. Now what you have to do, you have to give some notations. These are called as Bose notations. So see, here I will be giving P as the notation between this span and this span. So that is, in short, it is RA. And second notation Q. So force between P and Q is 20 Newton. So 20 Newton can be represented as force PQ. Then I will call it as R. So after 40 it is R. So 40 lies between Q and R. So I can call it as force QR. then S. So 10 Newton lies between R and S. So force RS is 10 Newton. And second last one is T. So PT, when I am calling it as PT, means it is reaction at A, and when I am calling ST, it is reaction at B. So likewise these notations you have to give. Now draw vertical lines at all the points. Then what you do? Now important, assume certain scale. Suppose you are assuming 1 centimeter is equal to 5 Newton. So this force is 20 Newton, or say 1 centimeter is equal to 10 Newton. So what you have to do? For 20 you have to draw a vertical line of 2 centimeters. So here I am drawing vertical line of 2 centimeter. It is force PQ, that is 20 Newton. So see, this is P and this is Q. So vertical, because this force is vertical. Now from this Q further you extend it to 40 Newton. So my scale says 1 centimeter is equal to 10 Newton, means draw a line of 4 centimeter. So I am drawing a line of 4 centimeter. I am calling it as R. Next, similar way, draw a line of 1 centimeter from R. So it will be representing 10 Newton and give the name as S. So it is RS. RS is 10. So this is RS is 10. Now somewhere here you draw a point. Anywhere call it as point O. Now join all these points to O. So first PO, second QO, third RO, and fourth SO. Now take PO, parallel to PO, draw first line here, parallel to PO. So I'll draw this as parallel to PO. The name will be given PO. Second, parallel to QO. This is QO. Shift it here, parallel to QO. From this point, draw a line parallel to QO. So this is QO. Then parallel to OR or RO, draw a line here, RO. Similarly, parallel to SO, draw parallel line here. So this will be called it as SO. Now what you do? Join the first point and the last point. So I am drawing a line here. Same, parallel to this line, you have to draw a line from this point in this diagram. So say it as TO. So you just draw the line parallel to this. So where it intersects this vertical line, then from here you can give the name to this as T. So PT is called reaction at A. See here, PT, force PT. P and T च्या मध्ये काय आहे? A. So that is reaction at A. And TS, T and S. In between T and S you have got RB. So it is TS is nothing but reaction at B. So this is called as graphical method to solve or to find the reactions. Now you can continue this line. Again you can continue the last line and then drop a vertical line from this point. So this gives you the location of resultant of these forces. This is called PT is equal to RA and ST is equal to RB. Now here this diagram is called as funicular diagram, this diagram is called